The next development in the model of the atom is a quantum mechanical model. So we'll go over a couple of the problems with Bohr's model and then address the wave-particle duality of matter, which helped contribute to the next model, Heisenberg's uncertainty principle, and finally get to the wave-mechanical model and talking about something called orbitals. First of all, with Bohr's model, recall that we have a nuclear atom, thanks to Ernest Rutherford's gold foil experiment, and Bohr contributed the idea of quantized energy levels. So we have these electrons have the potential to be in certain energy levels, discrete energy levels, but not at any random energy. So again, that was Bohr's model of the atom. The problem with Bohr's model as well as Rutherford's model is that the electrons being charged particles that are constantly moving should continuously give off energy, which means that they would end up spiraling in on the nucleus. So even with Bohr's model where there are discrete energy levels, those electrons would spontaneously fall from one level down to a lower level and eventually collapse in on the atom. Part of the solution to this problem came from Louis de Broglie, who showed that much like light could have a particle nature to it, the photon, and a wave characteristic as well, that matter could also have a wave-particle duality, that it can both have a particle nature and a wave nature. So what we want to do is think about in our mind then is rather than an electron circling around the nucleus like planets around the sun, that the electron would have a wave component to it as well. And this is kind of a physics concept that where is the particle in that wave and where does the wave exist? The wave exists over that entire region of space, and and the particle then would be felt over that entire region of space as well. And so this kind of led to a new way of thinking about what the electron was doing. At the same time, Erwin Schrödinger was trying to come up with an equation that would describe the motion of the electron around the nucleus, much the same way, again, that we had equations that would describe the motion and the position of planets around the sun. Obviously, it's kind of a complicated formula here, but a formula nonetheless, similar to if you had an equation for a line, you could graph that. Well, if you graph this function, you get a three-dimensional chart. So again, it looks very, very complicated, but we can kind of make some assumptions and work with this and get some real good understanding of the atom out of this. Now then along came Werner Heisenberg, and what Werner did was mathematically he showed that it was impossible to know both the position of the electron and the motion of the electron at the same time. And this is known as the uncertainty principle. Basically, if you were to measure one or the other, you would interfere significantly, and the uncertainty in your value would be greater than the actual size of the atom. In other words, the position of the electron, your uncertainty in that would be larger than the atom itself. What this did then was it led us away from finding an equation that would describe the exact position and motion of an electron at any particular time to try and understand the general area where we're likely to feel the presence of that electron. Now, fortunately, all of the work that had been done prior wasn't for naught. Turns out that if you take Schrödinger's wave function, which was given the symbol psi, as opposed to, like, for instance, a y, if we take that wave function and we square it, that wave function squared gives us the probability function. So that probability function is then going to describe a region in space where we're most likely to find the electron. It's going to where the value for that function is high, there's a greater likelihood of finding the electron in that particular area. What squaring the Schrodinger equation does then is create what are called orbitals. Now, orbitals are regions in space where we're most likely to feel the presence of the electron. Now, obviously there's a problem with using the word orbital here. You hear the word orbit and you immediately think of planets circling around the sun. And that's not what you want to think about here. When you hear the term orbital, you want to think of a region in space. And so we'll take a look at a couple of these. But you want to not think about the electron as a particle moving around the nucleus, kind of like planets around the sun. So the simplest wave function is basically a pattern of, or describes a pattern of dots. Obviously the nucleus is positive, so the function here is going to be most concentrated near the nucleus. That's where you have the highest probability of finding an electron. So this would be if you had one electron in an atom. There's always a possibility, when you look at probability, there's always a possibility of that electron being infinitely far away from the nucleus. So how do we deal with that? Well, we have to set some boundaries at some point. So usually what we do is we say, all right, well here's our probability function. But what I'm going to do is I'm going to say, if I take and make a boundary that contains roughly 90% of the values of that function, that is the region in space I'm going to call this orbital, right, rather than including all of space. So there's always probability of being outside of that, but we can set a boundary for it to exist there. Now, these orbitals are related to the energy of the electrons. As the energy goes up, we end up with some more varieties. First off, remember we have Bohr's principal energy levels, n equals 1, n equals 2, n equals 3, etc. Well, this simple Schrodinger equation, orbital, if we go up to higher energy levels, what we do is we create spaces that are larger and larger for those electrons to occupy. Another thing happens is that as we go up in energy, we also create some other shaped orbitals. So that function now, instead of describing a simple sphere, describes a region in space that looks something like a dumbbell shaped. So you can see that over here on the left. That's that generic, kind of dumbbell shaped orbital. These orbitals, and because it's different than a sphere, these orbitals can actually be oriented in the three different orientations of space, the x, y, and z planes. So you have three of this type of orbital at any particular energy level. These are called p orbitals. The spherical orbitals were s orbitals. And the way we want to think about these is that these are going to be the regions in space where we're going to find the electrons. We're going to end up putting electrons into these regions in space, these orbitals, much like you might put people into a home. So there's rules for filling the electrons in, and we'll go over those. But you're going to basically look at these as places to put electrons. And each of these orbitals can hold a maximum of 2 electrons. As we go up higher in energy, we'll get even other types of shapes. So these orbitals, and there are 5 types of these orbitals. These are d orbitals. And all 5 of those d orbitals would have the same energy. And again, even though they have multiple lobes on them, each one only holds 2 electrons. Now, to help us kind of organize this a little bit more, rather than drawing those orbitals all the time, oftentimes what we'll do is we will draw what are called box diagrams for these. So you can see here a schematic of the first three of Bohr's energy levels. The first level, n equals 1, which only has the s orbital, n equals 2, which has s and p orbitals, n equals 3, that has s, p, and d orbitals. And again, what we'll do is we'll work on placing electrons into these orbitals, but we want to kind of keep in mind what those orbitals look like, those regions in space. Here are the rules for placing the electrons into the orbitals. First of all, the Aufbau principle states that we're going to put the electrons into the lowest energy level first. The Pauli exclusion principle, we call that electrons are going to go into, we're going to put 2 electrons into each orbital. They have to have opposite spins when we put 2 electrons into the same orbital. So we're going to denote spin by an arrow up. So it would represent 1 electron. If we were to put a second electron in the same orbital, we would put it with a spin down. And Hund's rule states that if you have the option of putting 2 electrons into a single energy level, the electrons are going to spread out into different orbitals, if they can, rather than doubling up in the same orbital. So we'll get some practice on doing these things in class.